night, everyone, and their teachers and partners. My name is Carlos Castro, and together with my colleague Nelson Campbell, we will present an external economic analysis and comparison of biomass and fossil fuel conversion processes. This work is based on research by Nakai, Saibin, Shao, and Lowe, and others authors about this paper, but adapted to our study. The main idea is to compare energy, exergy, costs, and environment performance of different technologies, which are then focused on biomass, pyrolysis, and syngas production. By the end of this presentation, we hope you will to see not only the technical difference, but also the sustainable advantage for using biogas instead of fossil fuels. General objective. The main objective for this presentation is clear. We want to analyze in detail 2K process, biomass pyrolysis, especially corn storage, and syngas production from coal, natural gas, and biomass. This study combines four perspectives: energy efficiency, exergy efficiency, economics, and environmental impact. This integrated approach allows us to see not only the numbers, but also where process loss efficiencies, where costs are high, and where emissions are critical. The goal is to identify opportunities for optimization and to show which processes are more sustainable for the future. The structure of the presentation is divided into 5 main parts. First, introduction and context. Second is the methodology, analysis, and third, detailed analysis of biomass pyrolysis. 4. The exergent economic comparison for syngas production. Finally, discussions, conclusions, and recommendations. This logical order takes us from theory to results and to practical implications. Okay. Introductions, energy and environment background. Biomass is one of the most abundant renewable resources on Earth. For example, corn storage has a global potential of more than 1 trillion tons per year. When converted, biomass produces value products such as bio-oil, biochar, and gases. This reduces dependence on fossil fuels. Another important product is syngas, which is the basis of the production of the DMI, dimethyl ether. DMI is a clean alternative fuel and is the global market is expected to grow quickly. At the same time, climate change pushes to the need for low carbon technology. Biomass is carbon neutral, while coal generates very CO2 emissions. Now let's see the specific objectives. First, evaluate energy and exergy efficiency. Two, energy shows how much of the input energy becomes useful products. And three, exercise efficiency is more advanced because it includes the quality of the energy and identifies irreversibility. Second, analyze the economic costs. This shows which steps make the process more expensive. Third, compare environmental impacts, especially CO2 emissions and global warming potential. Finally, provide recommendations for industrialization optimization. In this slide, we are going to speak about the modeling and simulation of the process. We used Aspen Plus software. For pyrolysis, we simulate a plant processing thousands tons per year of the cornerstone. For syngas production, we use gratification and three reformer models. The error was less than 2.5%, so the results are relevant. Key assumptions: a reaction the reaction temperature of 500 degrees Celsius, normal ambient conditions, in the cost $2 for gigajoules for biomass and 1.15 for coal. This simulation provides a device to the energy, exergy, and cost analysis. The simulation obtained the results about the into show in the graphic. In this case, energy and exergy analysis, we applied the first and the second law of the thermodynamics. Energy efficiency is the ratio of produced energy to input energy. Exergy efficiency considers physical and chemical exergy. It allows us to see where energy is destroyed or lost. In pyrolysis, the largest energy destruction happens during combustion. The second largest loss comes from pyrolysis itself. This analysis shows us the weight points of the systems. Now the exergy economic analysis SPECO. We use it to SPECO method, which has significant cost to energy flows. The factor if key represent non-energy costs such as equipment, maintenance, and labor. The factor if key show the cost difference between the inputs and products. For example, the oil has a cost of $0.405 per kilogram of exergy. Biochar is more cheaper, only $0.055 per kilogram. This tells us where the process is expensive and where optimization is needed. In In this slide, finally, the environment analysis has we measure CO2 emissions for tonne of the syngas or per megajoule of product. We also calculate the global warming potential. Even though biomass is carbon neutral in combustion, we must include emissions from utilities such as electricity and heat. This connects the technical result with environment high performance. In this case, the pyrolysis system results. The system has four states. The system pre-torrefaction, pyrolysis, condensation, and combustion. Scale industrial 10,000 tons per year of corn store. Main products by oil, biochar, and gas. This shows how agricultural residuals can be transformed into valuable products instead of being waste. The total energy efficiency of the system is 65.5%. The largest destruction happens in combustion. The second largest is in the pyrolysis stage, and torrefaction is condensation have lower losses. Improvements should focus on combustion and pyrolysis. In pyrolysis cost. From the cost perspective, condensation is the most expensive step. Its key value is 0.71 because of the equipment is complex. Pyrolysis has 0.49 and torrefaction has 0.39. Product unit cost bio-air $0.005 per kilogram and biochar $0.055 per kilogram. In this slide, pyrolysis environment, the global warming potential of the system is 0.192 kilograms for CO2 equivalent per megajoule. And the largest contributions comes from pyrolysis, but overall emissions are low thanks to biomass neutral. Syngas key results. In quality gasification, with air steam had the highest energy efficiency, 68.6%. Methane 3 reforming with oxygen steam have had the highest energy efficient, 62%. Biomass gasification with an air steam had the lowest unit cost, $0.54 per kilogram. Biomass gasification with oxygen steam had the lowest cost in CO2 emissions, 2.83 tons for ton for syngas. And discussion. The slide show us the discussion, and there is no perfect process. Biomass is sustainable with low cost and emission. coal has high efficiency but also very high emissions, and pyrolysis condensation is the economic bottleneck. In syngas production, optimization should reduce excessive destruction in combustion and integrate CO2 and tree reform. Economy biomass is attractive but needs subsidies to initial investment. Environmental biomass supports the United Nations goal. The conclusions, main conclusions are biomass gasification is optimal in cost and environmental impact. Corn storage pyrolysis reach 65.5% efficiency. There are no universal best process because the choice depends on priorities, for example, efficiency, cost, or sustainability. Biomass gasification is optimal in cost and environmental impact. Corn storage pyrolysis results 65% efficient. Recommendations. Finally, recommendations. Prioritize biomass for sustainable projects. Perform life cycle assessment before implementation and invest in research to reduce if key factor in critical components, especially condensation. Promote policies and incentives for renewable energy. Thank you for attention.